right, are we rolling? If everyone would please lend me your attention for a second. Dr. Dale Partin is my predecessor as first vice president. He is an amateur astronomer and although retired, a professional astronomy educator at Macomb Community College. He has bachelor's and master's degrees in physics, a Ph.D. in electrical engineering. He has over 80 scientific publications and 38 patents. He is a fellow of the American Physical Society and a member of Sigma Psi and of the American Scientific Affiliation. He claims to be retired, but he is the busiest man I know. So I give you Dr. Dale Partin, measuring the speed of light.
I'll try to pull a fast one on you tonight. So let me tell you that back in 2013, I was thinking that I needed a project to keep me, excuse me for a moment, I just remembered I have my red dot pointer here someplace. There it is. I needed a project that would ensure that I kept going out and doing astronomy, that I thought would be helpful to me. And I like to measure things. So I picked a project that turned out to be way harder than I expected. And this is it. What I decided to do was to try measuring the speed of light the way that it was originally done for the first time, using one of the moons of Jupiter. I pronounce it Io. I think some people call it Io.
Either one, they say.
Either, is that what they say? Either one.
Or either one.
Anyhow, so I knew that this was how the speed of light had first been measured, and I decided to give it a try using Io. And here's a picture of Io. It's of the 4 moons that Galileo discovered, Io is the one that orbits Jupiter the closest to Jupiter. And due to tidal interactions, it gets quite hot, so hot that there are volcanoes on Io. I just took a piece of that and blew it up, maybe you can see that. Spewing sulfur out into space and comes back and settles on the ground, and you get various colors of sulfur depending on various conditions that it deposits at. So, you know, obviously, I think everybody here knows through an amateur telescope here on Earth, you can't see any of this at all. Io is pretty much just, it looks like a star. Don't tell me my down arrow isn't going to work. It's not working.
Enter.
Enter. Help. Technical help.
Aha. You did it.
Okay.
That's not very satisfying.
Well, it'll do. So, this is a picture that I just pulled off the internet of Jupiter and the 4 moons that Galileo discovered. You think that would work? Try it. I didn't think I would need to use the remote to advance slides. But that works. Okay. Thank you. So here Jupiter is very overexposed, so that the moons look fairly bright. And the point of this slide is to say each of these 4 moons, Io, Europa, Ganymede, and Callisto, all 4 of them are precision clocks. Their periods are extremely precise and can be used to measure the speed of light if you know how to do it. I'm going to take you through how to do it as part of this presentation, but I'm essentially not going to have any mathematics. I'll give some explanation, and if you get it, that's great. If you don't, it's okay. It's okay, don't worry about it. So I like, you know, when I do a project like this, I'm interested in the history of the thing that I'm doing. Galileo, back in January 1610, was doing some observations. He was an Italian astronomer, and he had just made his best yet telescope, 20 times magnification. He later made one, I believe, at 30 times magnification, but this was probably significantly better than any other telescope in the world at the time. And he happened to look at Jupiter one evening and saw some stars near Jupiter. So here is a picture of his actual notes, and this is sort of a translation of those notes into English. Here on the 7th of January, this is Jupiter, and this says, I can't read that, one of them says west and the other east, and he saw these 3 stars, and it kind of struck him that those stars were close to Jupiter, fairly bright, and lined up with Jupiter. And on the 8th, he happened to look back at Jupiter, and now he saw 3 stars all off to one side. On the 10th, I think the 9th was clouded out, but on the 10th, they looked a little different. On the 11th, a little different, and so forth. And he started getting really, really excited because he realized what he was seeing. He was seeing these moons that he realized these were not actually stars, but were what we today would call moons of Jupiter, orbiting Jupiter with the plane of their orbit perpendicular to the line of sight. So they appear to be moving back and forth in a line, but they're actually going around Jupiter. That was a major discovery. Up until that point, a lot of people thought that everything up there orbited the sun. Copernicus had said, no, that's not the case, but
Earth.
A lot of people, did I say the wrong thing?
Earth. Everybody thought.
Yeah, I'm sorry, yes, everybody thought everything orbited the Earth. Thank you for the correction. Copernicus had said, no, everything except our moon is orbiting the sun. That didn't go over too well, even among a lot of astronomers, because the evidence was not at all conclusive at that point. So 2 months later, in something, this is, I guess, the Italian name of a publication in English, we would call it Starry Messenger. Galileo published this. He said, I should disclose and publish to the world the occasion of discovering and observing 4 planets, he called them. Again, in today's terminology, we would call them moons. Never seen from the beginning of the world up to our own times, their positions and the observations made during the last 2 months about their movements and their changes of magnitude. And I summon all astronomers to apply themselves to examine and determine their periodic times, which it has not been permitted me to achieve up to this day. He didn't know, He hadn't figured out how long it took each of them to go around yet. On the 7th day of January in the present year, first hour of the following night, when I was viewing the constellations of the heavens through a telescope. This was a new thing. It's only about a year old at that point since it had been invented. The planet Jupiter presented itself to my view, and as I prepared for myself a very excellent instrument, I mean, it was not a very excellent instrument. I mean, the $54 thing that Jonathan Cade started was way better. But
1610.
For the times.
1610.
yeah, but this was 1610, right? And in 1610, this was by far the best telescope in the world.
One of the few.
Yeah, and one of the very few. It was sort of one up from holding 2 eyeglass lenses up of different prescriptions, right? That's how the telescope was basically invented. I noticed a circumstance which I had never been able to notice before, namely that 3 little stars, small but very bright, were near the planet, and though I believed them to belong to a number of the fixed stars, yet they made me somewhat wonder, because they seemed to be arranged exactly in a straight line, parallel to the ecliptic, and to be brighter than the rest of the stars. When on the next night, led by some fatality, I turned again to look at the same part of the heavens, I found a very different state of things. There were 3 little stars all west of Jupiter, and nearer together than on the previous night. I think that was where he got excited. And the 9th was clouded out, I believe. I therefore concluded and decided unhesitatingly that there are 3 stars in the heavens, he later would up that to 4, moving about Jupiter as Venus and Mercury around the Sun, which was at length established as clear as daylight by numerous other subsequent observations. These observations also established that there are not only 3 but 4 bodies performing their revolutions around Jupiter. Oops. I guess that was the end of his article. So, you know, I can feel the history of the moment. I can feel the excitement of the discovery, and you know, to me that makes it interesting to follow in footsteps of someone like that, and those who came after him who pushed this to measure the speed of light. So the next step that I can find happened in 1616, just a few years later. King Philip III of Spain offered a prize for anyone who could find a way to determine the longitude of a ship when it was at sea. Finding the latitude is not as difficult. If you can measure the angle up to the North Star, that's approximately equal to your latitude. So in 1616, Galileo proposed to do this by precisely timing when a moon of Jupiter went in or out of the shadow of Jupiter. If the time of an eclipse could be determined, then longitude could be found. I'm not going to walk you through how to do that, but it is correct that if you could precisely time those eclipses and knew when they should happen, then you could, from that and doing a measurement on another star, you could find your longitude. However, Galileo's predicted eclipse times were not very accurate. Probably partly because of his telescope wasn't that great, but also because he didn't know it, but the eclipse timings were not always the same. Something was changing them. He didn't know that. That came later. Also, a ship at sea is not a very stable platform for making telescopic observations. To see those, you need a telescope to see them very well with reasonable magnification, like 20x. I know you can see them with binoculars, but it's more difficult, especially if you want to see exactly when a moon goes into eclipse. You know, fairly high magnification, and if a ship is rolling or something, you know, you'll get nauseated.
Pardon me, Dale?
Yeah.
Do you know what Galileo's proposal for dealing with the issue of keeping them in a telescope sites?
I don't think he had a solution to that.
He did.
Pendulum.
He had two gigantic spheres with mercury in between them that the sailor would sit inside.
Oh my goodness. I hadn't heard that one. With improvements, this method for getting longitude could be used on land. And so at that point you could do cartography, map making with accurate longitudes as well as latitudes. So 50 years later, an Italian astronomer named Cassini had observed the moons of Jupiter. He discovered discrepancies in his measurements that he initially thought were due to light having a finite speed. Descartes had earlier argued that the speed of light was infinitely large. I don't know if that's why he was reluctant to follow through, but as far as anybody knows, he never went on to determine the speed of light based on his data. However, he had been collaborating with a Danish astronomer named Ole Christensen Roemer. There are various ways to spell Roemer's name. Sometimes I find it as R-O-E-M-E-R. And so he had been collaborating with him in some of these measurements, and they did demonstrate that they could measure the difference in longitude between two locations by timing eclipses of Jupiter's moons. So this is Roemer. He got the bug to stick with doing these measurements on Io and continued observations for 8 years. He verbally presented his results to the French Academy of Sciences, but never published them. A reporter heard his presentation and published a brief account of the presentation. I've read that the reporter clearly didn't understand what Roemer was saying very well, so the account is a little bit garbled, but it's clear that Roemer did make those observations. While he thought that anomalies in the timing of eclipses of these moons were caused by the finite speed of light, he did not determine the speed of light from his own measurements. That was done by Huygens. A Dutch astronomer, Christian Huygens, asked Roemer for a copy of his data. Using data for Io, he calculated the speed of light. His result was 220,000 kilometers per second.
140,000 miles per second. 140,000 miles per second.
This is what I read.
So that's the kilometers. I'm saying translated to miles.
Oh, to miles per hour.
140,000
Okay.
miles per second. You're welcome.
The speed of light, I'm going to stick with kilometers per second.
Fine.
Speed of light, my prerogative, right?
You got
The speed of light is a nice round number if you round it off a little bit. In these units, it's 300,000 kilometers per second, 186,000 miles per second, if that's your preference. Anyhow, I look at those numbers and you might say, man, he was way off. That's not what I see. As a physicist, when I see this, I think this was fantastically good. Fantastically good. I mean, this is the first ever measurement of the speed of light. I mean, quite a few years ago, I found out how the ancient Greeks had measured the distance to the moon and the distance to the sun and the size of the earth, and I replicated all of those measurements. And they had the size of the earth and the distance to the moon reasonably accurately, but their distance to the sun was off by a factor of 20. And that was fantastically good. Okay? Because nobody had the faintest idea how far the sun was. The best I could do with my amateur astronomy equipment was a 30% error in the distance to the sun, but I had nicer stuff, right? So I think this was a fantastically accurate measurement for the time. I have the greatest respect for what they did, especially after trying to replicate this, as you will see. So Io orbits Jupiter faster than the other moons, the other Galilean moons, and has eclipses more often, therefore. So it's the best moon of Jupiter to use for this study. You could, in principle, use the other Galilean moons to do the same thing. You'd spend your whole life trying to get good data, especially in Michigan. So how does this work? How do you get the speed of light out of these measurements? Recall what I said earlier. Io orbits Jupiter like a precision clock. Here's the orbit of Io going around Jupiter. Here's the sun. Here's the orbit of the Earth and the shadow of Jupiter, so that Io can go in and out of Jupiter's shadow. So the Earth is orbiting the sun, so we're not viewing these eclipses and emerging from eclipses from a stable position. We're moving. In fact, we're moving faster than Jupiter's moving, a lot faster. So let me walk you through the rationale here. If you imagine that the Earth was at position G here, and it just stayed there for a while, and Jupiter stayed where it was for a while, then every so often, the period of Io is roughly 1.7 days. So every 1.7 days, you would see Io come to this point, and it takes Io a little over 3 minutes to go from just touching the shadow of Jupiter to being immersed in the shadow of Jupiter. So you see Jupiter dimming, you'd see Io dimming, and then gone, okay? And then 1.7 days later, or more likely a week later, you have to wait until this happens again when it's at night. You'd see Io again do this, and if you precisely timed the moment that you last see Io and it disappears, and you divide by the number of orbits, you would get the period, the true period, precisely. Okay? However, things are not standing still. I should mention that every time Io goes into the shadow of Jupiter, it takes time for the light that you are seeing from Io gets to the Earth. Quite a lot of time. It can, depending on where these things are, it might be, for example, on the order of 40 minutes. Okay? So when you see Io disappear in the Jupiter shadow, that would have happened many, many minutes earlier. It just took that long for the light to get to you. Okay, now let's remember that the Earth is orbiting the sun, and let's neglect the motion of Jupiter because the Earth is moving faster. Just think about the Earth's motion. If you are at point F and you see Io disappear into Jupiter's shadow, And then a week or two or a month later, you're here, and you again see Io disappear. You're closer to Jupiter, so it takes the light extinguishing from Io less time to get to you at this point than it did to get to you at this point. Light traveled this much farther to get to you here than it took to get to you here. And it takes light some period of time to travel that distance. So when you calculate the period of Io based on your observation there to your observation there, it looks like Io speeded up in its orbit around Jupiter, because you see Io disappear sooner than you would have if you stayed here. So if you measure the period of Io this way, from here to here, you're seeing a speeded up period of Io because of the finite speed of light. So you could say, wow, I know how fast the true period of Io is, and I see it speeded up, I do this stuff, I can calculate the speed of light. The problem is you don't know the real period of Io. You don't know it. Back then you didn't know it. So what you do is you come over here half a year later, and you do a measurement here where you see Io come out of shadow, and then you do the same thing several orbits of Io later, here, and now it takes light longer to get to the second measurement point. So it looks like Io slowed down in its period. Okay? Now if you don't understand that, it's okay. It's okay. Don't worry about it. All right. Point is, the period of Io looks like it's speeded up when you were doing observations approaching this, like it slowed down here, and from the difference, you can calculate the speed of light based on calculating this distance and the difference in timing of the period. Okay, that's how you do the measurement. Now I'm going to step back to 1997, when I first got into astronomy and first joined this Warren Astronomical Society. I got my first telescope, and I got the idea of measuring the periods of the moons of Jupiter. So I measured them as a project. Here was my data taken between July 29 and August 27, 1997. What you're seeing here is the horizontal scale is time in hours, from 0 to 800 hours. So this is, I don't know, I think it was, yeah, it's about a month. What you're seeing here is the angular distance of each moon from Jupiter. The center of Jupiter is at 0, and let's see where, yeah, these are in radical divisions. I have a special eyepiece that you can measure angles with it. I'll show you that in a moment. So, first night I did measurements, I saw moons of Jupiter, measured how far each of one of them was from Jupiter and whether it was on one side of Jupiter or the other. The next night they were scrambled around. I didn't know which one was which, you know? I mean, they moved overnight, right? And so I had times when I would stay up half the night tracking these moons. You can kind of see them move every couple hours or something. One night, I was up all night doing this, and I saw one of the moons come in, disappear, I forget if it was in front of Jupiter or behind it, and then reappear 2 or 3 hours later on the other side of Jupiter.
So each one of those dots is an observation?
Yes.
Okay.
So I finally figured out which moon was which, I wouldn't let myself look at sky and telescope or anything to cheat. I wanted to do this by myself. And I gradually figured it out. And then, you know, some nights were cloudy or I didn't do it, but every so often I would go out and do measurements. And then here's a little mathematics. Don't worry about it if you're not into mathematics, but I used a computer and fit a curve to each one of these moons. This is Callisto, the one that takes the longest to go around Jupiter and goes out the farthest. The red one is Io, goes much more quickly back and forth around Jupiter. So I fit each of those 4 moons data with a sine wave, a sinusoidal wave. If you don't know what that is, it's okay. It's just a wave, okay? A wave, like this, right? That kind of wave, right? And use some statistics to get the best fit I could. Here's my data. This was my period for Io. A more accurate data that you can look up online has a 9 here instead of an 8, for example. Io, Europa, Ganymede, and Callisto. And I looked at this data and I noticed something funny. I mean, I have a head for numbers, and I can look at those numbers, and this number is almost exactly twice that number. And then I noticed this number was almost exactly twice that number, but this one was not twice that number, right? So I calculated the ratios. The period of this one divided by that one is 2.006. So those 2 moons are in resonance with each other. The period of this one divided by that one, 2.012, another resonance. The other one, I would say not in resonance. You could say that's a ratio of 7 to 3. But that's, you know, is that a resonance? I don't know. But I didn't know this before I took this data. Now, I estimated, and I'm not going to go into how I estimated that the precision of these measurements was about plus or minus 0.5%. So, for Io, with this period, plus or minus 0.5% of this amounts to plus or minus 0.009 days, which is plus or minus 13 minutes, or plus or minus 760 seconds. I need more than 100 times higher precision than that to do the measurement I want to do to get the speed of light. That's why you get into timing eclipses. Now, in my study in 1997, there were some nice things about that study. It's rather easy to do for these reasons. And none of these apply when you're doing eclipses of Io. Okay? This was wonderful. This was fun. This was easy. You could take data anytime Jupiter and its moons were visible. Right? As long as you can see them up in the sky, you can take data on them. Intermittent clouds were not a problem. Data could be taken in between clouds. There was no precise time when you needed a clear sky. Even poor seeing, if it wasn't too poor, was usually not a problem as long as the moons could be seen and their positions measured. And several data points could be taken throughout the night, every couple hours or something, if desired, to track the motions of the moons so you could get a sense of which one was moving toward Jupiter. I mean, the first 2 or 3 measurements is like, which one is which, right? From one night to the next. This is very similar to the eyepiece I used. The one I had was made by Celestron. I still have it. and use it sometimes for things. But I don't think it's for sale anymore. But it's very similar to this one made by Meade, which can still be bought. This is what you see when you look through it, and this is the scale I used to measure distances from Jupiter. I would, for example, center Jupiter at this end of the scale, and then measure distances to the various moons. Write down exactly the time that I did each measurement. In one case, one moon was, Callisto was a little too far from Jupiter, and have Jupiter here and Callisto's out here somewhere. So I had to do it, there was another moon in between, so I measured the distance from Jupiter to that moon, and then from that moon to Callisto. So not perfect. I did the best, most accurate measurements I could. I got reasonably good results. But John Dumar, who's here tonight, is now doing a similar study with higher accuracy using a digital camera. Okay? And who knows, maybe John, I know he's been, I challenged him to see if he could get the speed of light out of his data. And he really has tried. I still wouldn't absolutely rule it out from my discussions with him, but he needs a lot more data if there's going to be a chance to do that. We'll see. It's fun stuff to try. So I use Weather Underground, this website, to do forecasts. You can get a 10-day weather forecast. This one was from April this year. Just to show you how miserable things typically are. I'm sure I don't have to tell you. Here was my one chance in this 10 days to do this measurement. And this gray curve shows you the percent probability that there will be clouds. So on this one chance I had this night, early in the morning, but well before daylight, the probability of cloud cover was about 45%, and it was cloudy. Okay? Here, but these show you the chances, you know, the times when Io is going into eclipse. So only this green one was going to work. This one here I put in a different color, but it was too close to sundown. And, you know, if the sky isn't dark, then you can't see when Jupiter, when Io exactly is eclipsed, right? You got too much light background. So the only actual chance I had was this one, and it clouded out. Most of the time, things were clouded out.
Dan?
Pardon me?
Dale, I thought that percent cloud cover was the percentage of the sky that would be covered with clouds, not the probability of percent. Am I wrong?
My interpretation is the probability of being clouded out. Okay, but it can mean different things. I mean, one night I was out there. I guess I'll say it now. It's not unusual that I see 20% cloud cover predicted. So, you know, am I going to go out or not? And once it's down to 20%, I would usually, well, it depends on what time of night it's going to happen. If it's going to happen at 11 o'clock or midnight, even if it was 50%, I'd take my chances and set up my scope and hope, right? But I mean, I just clearly remember what happened recently. It's 20% cloud cover, but 3 o'clock in the morning, okay? All right, I will drag myself out of bed. And I've got trees on the east and west sides of my property. So unless it's to the south, I have to take my telescope, put it in the car, and drive somewhere. You know, I would pull up into somebody's driveway right, at 3 o'clock in the morning, turn my lights off, hope they don't wake up. I mean, you do this kind of stuff, you know?
A real grown-up astronomer.
Yeah. So I get my scope out, I look up, and it doesn't look good. But I set my scope up and I'm waiting, hoping, you know, you have to set the scope up and give yourself some time. So I'm 15 minutes early, waiting, and sometimes what 20% cloud cover means is there's a cloud here and a cloud here and a cloud over there, but 80% clear. That night, what it meant was there was a 20% haze over the entire sky. And what was so frustrating is I can look through the telescope and I can see all 4 moons. But they are so washed out that if I was doing my earlier kind of measurement, I could have measured their positions. But they're so washed out that once one of them starts going into eclipse, I can't tell when it disappears with any accuracy. And you need all the accuracy you can get on the timing. I mean, as close as you can get to plus or minus 1 second. I would set my watch every night before I went out. There's a way to set it from the National Institute of Science and Technology. So I get it to within a fraction of a second, and that became my time standard. And then I'd use a stopwatch. I'm looking through the telescope, you know, and when I see the moon disappear, and then I go to my trunk where I have a little light, and I watch for the next minute to come around and stop the stopwatch and then subtract the time from that. I tell you, I wonder what these guys back in the 1600s were using to keep time.
Yeah.
Yeah.
You know, that's something I looked into a little and I couldn't find it out. But I mean, I think what they ultimately were using was some kind of way of keeping time that was good for maybe an hour or two,
Pendulum.
and they would do it from based on when a star went over, something like that. That's the only thing I can think of. And I tell you, the craziest things happened. One night, I was set up in my front yard, and Jupiter is just as clear as crystal, right? And in my backyard, I had a pond. And it was kind of a cold night, and the pond water was still warm, and there was this like fog over my pond. But it was okay. It's in the backyard. I'm in the front yard. And I can see Io dimming. You can easily see it the last 2 minutes, right? I'm not that great at judging magnitudes of things, but I'm going to have to hurry. I can see it dimming, and then this little breeze comes. And it blew that fog over my pond into my front yard, and Jupiter is dimming. Just, you know, I'm within 1 minute of what is going to happen, you know, and I can't get it. I gotta pick this up. I'm sorry. Suffice to say, I tried to look in sky and telescope. You can skim that if you want. I'll just tell you what it says. It says, when I looked at when these events were supposed to happen in Sky and Telescope magazine, I see a time to the nearest minute. Not nearly good enough for what I need, but at least it told me when to look. But then I happened to look at their website, and the times would sometimes differ by a few minutes. And even the sequence in which different events of different moons would happen would be reversed. So I wrote to Sky and Telescope, and the response was, you know, these timings aren't instantaneous. They get their timings from somebody else. Maybe it's only, their time maybe refers to the center of the dimming. And that's assuming the official date is perfect to start with, which I doubt, one of the associate editors said. And I frankly don't know whether they compute the times based on the moon's centers, as though they were point objects, or taking the moon's disks into account. Our applet on our website uses somewhat simplified formula, frequently off by as much as 2 minutes from the Times magazine. He was surprised that some of the things are off by 5 minutes. I next found the website of Dr. Mark Showalter, senior research scientist at the SETI Institute. He was an expert in the outer planets and their moons and rings. And he had a website where you could get these things apparently very accurately, but my measurements typically differed by his predictions by more than a minute. So he and I went back and forth a lot by email. His last communication with me said, this is very puzzling. I suspect the problem is in the Jupiter viewer's definition of the shadow edge, which ignores the size of the sun's disk. That's a significant error, and also treats the Jovian atmosphere as an opaque edge, which it's not. He said he knew some astronomers who have observed eclipses of these satellites. I will see one of them in a meeting in a few weeks, find out if they have any explanation. He never got back to me, and we'd been back and forth several times. I let it go. I talked to our own Ken Burton, who is my local go-to guy for the best astronomy app that would have this kind of thing. He thought one of his apps, I think it was Sky Safari Pro.
Yeah, it's actually more improved, that's it.
Yeah, was quite accurate. All I can say is, didn't agree with my measurements at all.
I'm not surprised.
Pardon me?
I'm not surprised.
Not surprised, he says. So I wrote down some of the problems I had. Some of these I've already mentioned. You have to get up at some awful hour to do a measurement. I was often kind of drowsy. Weather reports were often uncertain if you'd be able to see it, so I'd have to make a no-go decision on do I get up and go out and set up and everything. I think I already said this stuff. You can set up in a pretty clear sky. Just this year, I remember, I went out and looked. It was going to happen at around midnight, so I stayed up and looked. I could see clouds way off in the west, but it was spectacularly clear. There's Jupiter. So I set my telescope up, and hurry up and happen. The clouds are coming, you know? And no fooling, I could see Io dimming when the clouds. It's happened a lot. One time I was out, I had to go set up somewhere else, and the sky was almost completely clear. There's a little tiny puff of cloud over there, and a little tiny puff over there. And I'm watching, and Io is dimming. And all of a sudden, Jupiter's dimming too. So I look, and here's this little cloud. Little. Clear all around it. And it blocked me for 34 seconds. And when it's past, Io is gone. You know, and I got up for this. Did I do all these? Yeah. It's easier to time Io going into the shadow. I gotta hurry. Going into the shadow of Jupiter than to see it coming out of shadow, because you don't know where exactly to look. And you get to this point where, is that it? Is that it? You know, I'm not sure. So I start counting 1,001, 1,002, 1,003, and at some point, if it stays there, I click it, and then remember the count, and, you know, do that stuff. The weather was sometimes very cold, especially the first winter I was doing these. My eyes would be watering. I can't hardly see, you know. The eyepiece would be fogging from being close to my eye. I'd have to keep a Kleenex handy, you know. Lubrication on the eyepiece focuser froze one night at -8 degrees Fahrenheit, and I hadn't gone out real early, so it was about to happen, and I didn't have time to go get another telescope and set it up. I never tried using that one again. My Meade 8-inch I used after that, but it was never that cold, so I don't know for sure if the lubricant would freeze. Another time, the stopwatch. I had an old mechanical stopwatch. It stopped working. And every time this kind of nonsense happens, that was that was a chance to get a data point. And you need at least 2 data points to get one time interval. And now and then I would simply forget. I got my first smartphone and I kept setting the app wrong on it to wake me up. And I have to say, Michigan is just not the best place to do this kind of thing. I think Roemer must have had better weather.
In Denmark.
No, he did most of this in Paris. Though he did a few measurements from Denmark. This just shows you a picture of Jupiter and Io. So here's my raw data. 5 years of data. Isn't that pathetic? It's pathetic.
Yes, it is. 5 years. 2 per year.
This is the period of Io in seconds, like 152,000 some seconds. And each of these data points means 2 measurements, right? So these periods are bigger than these periods. Why are they bigger? Because Earth was receding from Jupiter with Io emerging from Jupiter's shadow. So it made Io's period look longer. And here, Earth was approaching Jupiter, so Io would go into eclipse. That's why they're different. So then you play the game of, let's say the speed of light is this, and calculate how that would shift each of these data points. They would tend to move toward the center. But if you pick a speed of light that's too far off from reality, then these data points would move way up here, and these way down here. So you find out where they all meet in the middle. And for those of you that know some math, I did a least squared fit to kind of quantitatively measure what the best speed of light was. Treating speed of light as a variable. So that's my fit. Quite a bit of scatter here. From here to here is 5 seconds, right? So the scatter is, I think sigma, if you know about that stuff, was a little more than 1 second. 1.4 seconds, I think. And when I got the optimum fit, the value of C that gave me that best fit was this. And again, the correct speed of light is 300,000, very, very close to 300,000 kilometers per second. So that's about 10% high. I was delighted.
Yeah.
Now, I was on a website reading about Roemer, and I found 1 year's data from him. And I think it was his best year for getting data out of his 8 years that he did measurements. So I took that data, which was in a tabular form. So the blue is his raw data, and then the red is my fit to his data. So here, which is it? Yeah, Earth was receding from Jupiter here, and for these 3 blue points, Earth was approaching Jupiter. So when I played with the speed of light, I got the best fit with the red data points here, and got a similar optimal value for C. I don't have all of Roemer's data to use, but Huygens did, and he got this number, which again I think was excellent. I have, after having done this study, I have only more respect for what those guys did. I can't believe how many data points he got, but I think this was his best year out of 8 years that he got that much data. In summary, I spent 5 years doing these kind of things. I got a ballpark value for the speed of light using a technique similar to that of Roemer and Huygens. This is the way speed of light was measured for the first time. I think if one did video recording of these eclipses, you'd get higher accuracy measurements. And Arizona would sure be a better place. Thank you for your attention. Are there any questions? Yes, Brian.
Yes, how accurately did they know the size of the Earth's orbit then, and the size of Jupiter's orbit? You know, the moons went around Jupiter.
At that time, they were pretty close.
Pardon me?
At that time, they were pretty close by the end of the 1600s.
How did we know that?
So Huygens actually calculated the astronomical unit, but he made some simplifying assumptions that were based on numerological considerations rather than scientific ones, and basically guessed the astronomical unit almost dead on, despite not really having a good scientific method for doing it.
Yes.
Did you ever, or do you even need to consider the fact that Earth and Jupiter are in non-elliptical orbits?
Oh, no.
You have to do that.
I'm more concerned about the fact that Io is not in a perfectly circular orbit.
Correct.
There are several sources of error here that I didn't go into because I'm trying to keep this fairly light. But there.
How long? 95 years?
I mean, you can think about various corrections to the data. Yes, the non-circularity of the orbits of the planets. I mean, everything matters when you're pushing it this hard. Another thing would be, we're not exactly lined up with the plane of those moons, except on rare times of Jupiter's year. So when these moons go into eclipse, they're not eclipsing right on the equator of Jupiter. They're eclipsing at some other place. And that some other place is changing with time. So you do one measurement, and maybe 3 or 4 weeks later you do another. It's not hitting Jupiter at the same spot, or its shadow at the same spot, right? So there's stuff like that and more to be concerned about.
Have you read the book Longitude about how the Queen of England was concerned about determining longitude, and the scientific communities whose position was you measure the moons of Jupiter, use those for keeping time, but the competition for £1 million or whatever was won by a clockmaker.
Right. Harrington or Harrison? Harrison, I guess. Yeah, and we've had presentations
As
on
a matter of
that.
fact, mescaline almost prevented him from getting the
Yeah, that's a story in its own right.
Yes.
That's my history stuff.
Maybe one more question if somebody has one. If not, that'll do.